Hello and welcome to another video. In this video we're going to be working on count complete substrings from the last weekly LeetCode contest. This is the third problem. And I will preface this in saying this is definitely a hard problem, so if you weren't able to solve this, it's totally fine. There's no way it's a medium problem in my opinion. It's very unintuitive. So in this problem you're given a string word and an integer k. A substring of word is complete if every character in S occurs exactly k times, and the difference between two adjacent characters is at most 2. Return the number of complete substrings of word. A substring is a non-empty continuous sequence of characters in a string. So in this first example, the number of substrings here, so EE is a substring because the character E occurs twice. IG is a substring, and the whole thing is a substring, so there's 3. And then in the second one, all the A's is a substring, all the B's is a substring, all the C's is a substring, all the A's and B's are a substring, all the B's and C's are a substring, and the whole thing is a substring. So we have 6 total. So originally I was trying to do this by keeping track of like some kind of streak of how many contiguous substrings there are, but the problem is that I missed a lot of cases where something like even like BA can be a substring if like k equals 3. So there's really no way of doing that in a good way. And the other problem is, so let's just think about like a brute force solution, right? The brute force solution, let's say we have this like A, B, C. Brute force solution is just take every single substring, and the way to do this is you just take every substring that starts with one character or ends with a character. Let's say we'll say that ends with a character. So for example, we'll take every substring that ends with A. In this case, it's just A. And then we have to figure out like what's the count of each letter, and is the count of each letter 3, right? So it would be like this. This is not 1. Then we'll take like this. The count of A is 2. The count of A is 3. So this is 1 answer. And then for substrings that end with B, it would be like B, BA, BAA, and so on, right? And you would basically do this over and over and over, and then that would give us an n-squared solution, which is too slow. So another thing is, for this part is really easy, right? So they're basically saying that you can't have a substring that consists of characters that have neighbors that are more than 2 characters apart. So that part we can take care of easily. We can just go through our string and cut it into strings that actually are valid. So for example, let's say we have a string like, let's see here. So we have like A, B, C, and then here we have like G something, right? GHI or something. So we know immediately that like the C and the G can never be in the same string because the C and the G are too far apart. They're more than 2 characters apart. So then we know like our valid strings here would be this and this. So that's very easy. Anytime 2 characters are more than 2 characters apart, you just like end that string and start a new string. So we can separate our string into chunks, and that would basically satisfy constraint 2. And the way to do that in Python is you can just take the ord, which will give you the ASCII value of a character. And if the ord of one character minus the ord of the other character is greater than 2, then you just make that split. So now that we took care of this second part, which is like the super easy part of the problem, we need to figure out how to do this first part in O of n or n log n or something. And that's where we need to figure it out. And the way we're going to figure this out is we're going to look at kind of what we need to be doing, and then we're going to figure out how we can shorten it and get some intuition. So here we have this example of this first word where we have the index of every single character. And so like I said, what we really need to do is we need to, for every single character, we need to figure out like, is that whole substring, like let's say we're on this character, we need to get all substrings that end with this character and figure out like, is that an output? So for I, we'd have like I. For G, we'd have like GI. For I, we'd have like I, IG, IGI, and so on, right? Which would be n squared, which is too slow. So we need to figure out a better way to do it. So one intuition that we can have is, for example, let's say k equals, what does k equal in this case? I think it's like 2 or 3? 2. Okay, so if k equals 2, we know that, let's just think about like, what's the length of substrings that, and we also know that we're going to break our string down into strings where now every character has a frequency of no more than 2. So for one thing, we know that like, let's think of like the length of our substrings that have to be valid. If k equals 2. So if every character has to have 2 count, or 0, obviously, right? So every character is going to have a count of 2 or 0. That means, in this case, our substring length has to be divisible by 2. So we can already cut out like half of them. So let's say we look for all substrings that end with this character. We know it can't be just this character because that has a length of 1. And we need every substring to be a length of 2. So we can check like this substring, which would be a length of 2, then this substring, which is length of 4, and then that would be all the substrings that end with this character, right? So for I, there would be nothing if you're going from the left because you have to get length 2. For G, it would be this one. For this I, it would just be this GI. For this, it would be this one and this one. For this E, it would be this one and this one. And for this E, it would be this one and this one and this one. So we already cut out half, but that's still too slow. So we need to figure out a better way. And so a problem is our substrings can be very long. Like, let's say we have a substring like A, like a million A's, right? When we cut down our strings, remember, we're only cutting down our original string into strings that are close to each other into the alphabet. So we'll never have a substring that has like an A and a G right next to it. But if imagine our entire substring or 10 to the 5th characters is all A's, that would just be one chunk. And then for that, we can't just compare like every single index of the 1, -2, -4, -8, and so on. So we need to cut it down even more. So if we think about it, if the word consists of lowercase English characters, now we kind of know like what indices we need to check and what indices we can skip. Like for example, if k was 10, we can just subtract 10 every time, right? Because we're looking for substrings where the count of every character is 10. And so if the substring is length that's not a mod of 10, then we don't have to worry about it, right? Like if k is 10 and the substring length is 9, there's no way that can happen. But another thing we can notice is there's 26 characters, right? So the most characters we can have is 26. So let's think about the length of the longest possible substring we can have, right? Like let's say we're on some index. Let's say this is like index 1,000,000, whatever it is. You know, what's the longest substring we can have? Well, the longest substring we can have is 26 characters, where the count of every character is k, right? So if k is 2 here, even if our entire substring is A's and we're on index 1,000,000, we would never have to check that many because the longest substring we can ever have is only 52 characters, right? Like the longest substring we can have is going to have 2 A's, 2 B's, 2 C's, 2 D's, and so on. So now we know that actually for every index, all we have to check, we do have to check every 2, right, to make sure that it's still divisible by k. But the most we ever have to check if we're at some index, all we have to do is check 26 times k, right? For every single one. So we do like I minus k, I minus 2k, I minus 3k, I minus 4k, and so on. And that makes sense, right? Because we can't have any more than 26 characters, so the longest possible substring we can make is 26k. So let's take a look at this now and see kind of how this will work. And we have to simplify it down a little further. So let's first of all get these substrings. So let's say for every index, let's kind of walk through this a little bit. So like for this index, this is the first one, so we can't have a substring of length 2 or more. For this one, we can, right? And it would be this. And does this substring match our criteria? Then we're going to figure out how to actually check if we match our criteria quickly. But let's say our end index is here. The only substring we can make is this one over here, right? The substring of 2 characters. So we have to try 2, we have to try 4, and so on. So this 2-character substring obviously doesn't match our criteria because the length of every character isn't k. Now let's look at substrings that end over here. So substrings end over here. The first one is going to have 2 characters here. This obviously doesn't match our criteria, our top criteria. And the second one would have to have 4 characters, right? Because we just keep adding a k until we're out of bounds. Or sorry, until we have 26 k's. So 4 characters, we can't have that, so we don't have anything here. Now here, 2 characters, doesn't match our criteria. But 4 characters doesn't match our criteria, right? We have 2 G's and 2 I's. So this is 1, so we'll put a little 1 here. Then we'll go to the next index. So we'll try 2 character, doesn't work. 4 character, doesn't work, and we can't do anything else. And finally, for the last index, this is a 2 character, which does work. So we'll add a little 1, 4 character, which doesn't work, and then 6 character, which does work. Everything has 2. Okay, so now we kind of have the idea of roughly, let's write this down. So for each end index, iterate 26 times k, or iterate from k, like 1k to 26k, right? So k to 26k, whatever k is. So in this case, it would be 2, then 4, then so on. And figure out if that substring is valid. But now the problem is here, like, how would we do that? Like, let's say we're getting a substring of 2 characters. So this would be like would we just record it as we go or something? I guess we could, but that's still kind of slow because let's say k is like 1,000. Then we'd have to manually go through like 1,000 characters. And if we're recording as we go, we're still kind of like not really getting the whole point of we need to try to do this as fast as possible. So is there a way, given some start index and some end index, to know if this is in fact valid very quickly? And there is a way to do that, and it's very unintuitive. And it's going to be using a prefix sum. And the idea behind the prefix sum is basically if we just keep track for every single index, the count of every character, then if we look at 2 indices, in order for that substring to be valid, every character in this right part, if we look at the count of the character in the right part and the left part, the difference of that character either has to be, we can write that down. So for every character at right index, the difference of right minus left of that character has to either be k or 0. And let's figure out why that is. So if the difference is 0, that means the count of that character is the same, right? So if the count of that character is the same, that means it's fine. Because also keep in mind that our substring is going to be length of some multiple k, right? So our substring will be length of like x times k. So if the difference is 0, that means that character count, or that character is basically not in this substring, right? So let's see. Let's say we're over here and over here. Actually, no, let's not use that. Let's say we are. Where do we want to be? Let's say we're over here and over here, right? There we go. So let's say we look at the count of character I. The count of character I didn't change. It's 0, right? The difference is 0. So that means I isn't in this substring. And that's totally fine, right? So if a character isn't in substring, that still validates that the count is k, right? So it's either k or 0, obviously. So each character occurs exactly k times, but it can be 0. Like if you have AAA, like z is not in here, so the count of z is 0, but that's totally fine. So in order to have a valid substring, the count of every character has to technically not be k, it has to be k or 0, right? So if the count here is the same as the count here, that means the count in the substring between them is 0. That means the character isn't in there, which is fine. Now the last part is why do we need the difference to be k? So if the difference is k, that means every character that is in the substring occurs exactly k times. So for example, if the count of E here is 2 and the count of E here is 0, the difference is k. That means E occurs exactly k times in the substring. So it's a little bit tricky, but that's kind of what it is, and we'll go through some examples to see this a little bit better. So once again, if the difference is k between 2 different indices, that means in that substring, the character occurs k times, which is what we want. And if the difference is 0, that means the character doesn't occur at all, which is totally fine, right? So every character that is in the substring will have a count of k. If not, we can just like break or something, right? So let's kind of show how this is going to work. So I showed this one -1 because what we're going to make is we're going to make a prefix sum, but instead of making an array, we're actually going to just use a hash map. It's going to be a lot easier. So in the beginning, we'll just have a hash map at index -1, and it will just have an empty dictionary, right? Everything will have a count of 0. Then at 0, I will have a count of 1. At 1, this is like a prefix sum, so you just take the previous and you add the current thing. So I will still have a count of 1. G will have a count of 1. Then here I will have a count of 2. And G will have a count of 1. Here we have I equals 2. And G equals 2. And finally, in this third one, we have I equals 2. G equals 2. And E equals 1. And the last one we have I equals 2, G equals 2, E equals 2. So we're basically going to have a dictionary of this prefixes where the key will be index and the value will be dictionary of letter counts. So like in our prefixes, we'll have like prefixes -1 is, this will just be an empty dictionary here, and so on. So then what we need to do is, and also every time we chunk up our word, like let's say we get to a letter like G or something that will index 6, then we'll just say, okay, we'll take our count and completely reset it because that's a new chunk. So we're going to process our entire chunk, get all the arrays from there, and then once we get to a new index, then we'll just reset our dictionary. So so this 6, what's going to happen is I'm going to make a new count. And at 5, I'll put this empty dictionary, right? And the reason I want to do that is because I'm going to have, before the original index, so whatever this leftmost index is, in this case it's 0, I'll make at index -1 a hash map of that's completely empty. That's kind of like in a prefix sum, you know, you can say like at index -1, we'll make the sum 0. That way we know what's the sum of like the entire array. So that's kind of the same thing here. Okay, so now let's walk through this algorithm. So essentially what's going to happen here is, over here, we're going to have a count of 1, and we're going to say, okay, let's just, instead of actually building up this whole thing, let's just see what indices we can go to. And we can go to every index that is up to -1, right? Whatever this original empty index is, but we can't go any more than k times 26. So in this case, we can't, and we're going to go by 2, right? Because we know that for a substring to be valid with k equals 2, it has to be length that's mod k. So in this case, we can't go anywhere because we'll be out of bounds, right? Like 0 minus 2 will be out of bounds, so we'll skip this one. Now over here, so we're over here, now we'll compare these two. So we're going to compare every letter to the right to the letters on the left. So we're going to say for I, the count of I is 1. What's the count of I over here? It's just going to be 0, right? So I didn't write it in, but in the empty dictionary, the count of every letter is going to be 0. So if it's not in the dictionary, the count will be 0. So because the difference in I is 1, that means that we know this substring can't be valid. Because in the substring, I occurs once and it needs to occur twice. So that's not going to be valid. So we're going to move on to the next thing. So we're going to, and we're going to do this, by the way, as we build it. So really what's going to happen is, we're going to like build this 0. We're going to build this, and then we're going to check the stuff before it. And then we're going to build the 1, then we'll check the stuff before it. Then we'll build a 2 and check the stuff before it, and so on. So let's go, so we're going to go to the 1 here. Oh, we already did that, right? So we're going to go to the 2. We're going to populate its location in the prefixes, and then we are going to loop backwards. So we're going to check, okay, what indices can we go to? We can go to this one. This is k away. So let's compare. So the difference here is 1. That means I occurs once in here. And so that's already not valid because we need I to occur twice. So we can't do anything there. And if we go one more, we'll be out of bounds. So now we're going to build the next one. So we'll build the 3. And for the 3, we're going to have this count. And we're going to loop again. So we'll check this one. So what's the difference in I's? Not valid. So this one doesn't work. So let's keep looping back again. So we can also go to this one. This is also in bounds. What's the difference in I's? 2, and what's the difference in G's? 2. So every single letter in here has a difference of k, or 0, right? So this is a valid substring. And we could do this in O of 1 time because we made this prefixes, right? We can just traverse and check this one and this one in O of 1 time instead of building this whole thing up. We can just traverse correctly. So that's going to be one of our results. So we'll have a 1 here. Then we'll keep going to the next one. And we're going to build it first. Then we will check over here. So I difference is 2, which is fine. or I difference is 0, which is fine because that means I doesn't occur in here, which is totally fine. Now G difference is 1, and so that doesn't work because now the G occurs once and we need it to occur twice or 0, so it doesn't work. Oh, and we forgot, we also need to check this one. Yeah, so we need to check over here as well, and over here I difference is 1, which doesn't work, right? Because it needs to be 2 or 0. Okay, now for the 5, we're going to build it. We're going to build up this prefix, then we're going to traverse backwards. So over here, I difference is 0, which is fine. G difference is 0, which is fine. And E difference is 2, which is fine. So this is valid. So we'll add 1 to the result. We will traverse backwards over here. And we'll compare again. So I difference is 1, so it doesn't work. And then we'll compare to the empty one. I difference is 2, G difference is 2, E difference is 2, so this is also valid. So our result equals 3. So that's pretty much how you do it. You do the prefix sum, and then you can, for every single index, you can traverse back up to 26k times. And now our complexity, we've reduced it from n squared to, for every single index, we can treat it as the end index. And for every single index, we will basically traverse back 26k times, right? So we'll just do like minus k, minus 2k, minus 3k, minus 4k, and so on. So our complexity here will be n times 26. Because we will build up 26 different subarrays and check them in O of 1 time. So it'll actually be more like 26. So it will be n times 26 because we'll build up 26 subarrays. And also for this comparison of every character, we'll also take 26. So it'll really be like n times 26 times 26. And because this is 10 to the 5th, this is like n times 500. And that would be like 10 to the 7th, which will barely pass. So this is another part of this problem is most solutions are barely passing or not passing because it's slightly too slow. So let's actually look at this one. So this is the final one we'll look at. Let's make it a little bigger if possible. And let's do this one more time and see exactly how this is going to work. So now we're going to build it as we go. So once again, we are going to have, this is just going to be empty. So anything empty will have a count of 0. So we're going to say, or what's k in this one? This was the second problem. So let's take a look. K is 3. The same kind of thing. We're going to traverse back. K equals 3 times now. So here it's going to be empty. Then here we'll have a count of a equals 1. Then we can't really traverse back because we'll be out of bounds. Here we'll have a count of a equals 2. Can't traverse back, we'll be out of bounds. Here we'll have a count of a equals 3, and we can traverse back to this one. So we're going to compare. This is the difference in a is 3, right? So that's valid because every difference is either k or 0, which it works. So our result will be 1 here. And this is a valid subarray. So that's fine. So 3 and, or not 3, 1, and delete this. Then we go to the next one and we'll say, okay, A is 3, B is 1. Let's compare. And so the first one we're going to compare to is over here. And this doesn't work because the difference in A is 2. So it doesn't work. So let's go over here. A is 3, B is 2. Let's compare again. So we can compare to this one. The difference in A is 1, so that doesn't work. Now here, A is 3, B is 2. B is 3. So we can compare to this index. So this one does work, right? Because the difference in A is 0 and the difference in B is 3, which matches our criteria where everything is a difference of either 0 or k. So we'll add 1 to the result. And now we can make one more comparison. So we compared 5 to 2. Now we can also compare over here because this is minus 2k, and then we'll be out of bounds. So over here, the difference in A is 3, difference in B is 3, which is also fine. So this is also a valid result. So this is going to be, it's going to have 3 results now. Then we're going to have A equals 3, B equals 3, C equals 1. And then we can compare again over here. So A is fine, but B is a difference of 2, which doesn't work. And we can also compare over here. A is not fine. A is a difference of 2, which doesn't work. So lastly, or almost lastly, we'll have A equals 3, B equals 3, C equals 2. We will compare to 4. A difference is fine. B difference is not fine. B difference is 1, so it doesn't work. We'll also compare to 1. A difference is 1, so it doesn't work. Finally, we'll have A equals 3, And it's kind of small, so sorry about that. There we go. So we'll compare 8 to 5, right? 8 minus k. A difference is 0. B difference is 0. C difference is 3. So that's fine. Valid result. Everything is valid. So difference 4 here. Now we will compare 8 to 2. That's going to be the next one. So A difference is 0, which is fine. B difference and C difference is both 3, which is fine. So here we have 5. Okay. And finally, we will compare 8 to 1, 2, 3, 4, 5, 6, negative 1, right? K minus 3, or 3k. And A difference is 3, B difference is 3, C difference is 3, so those are all fine. So we'll add one more to the result, so our result ends up being 6. So hopefully you can see how you do this, and then essentially anytime you find a new chunk, you just completely reset your prefixes array, and then you start recording at the new index. And before you record at the new index, let's say you reset at index 9, then you would say like prefixes at index 8 is a new dictionary again, right? And that's the idea. So we're going to traverse 26k times, but as soon as our index gets, like let's say our leftmost index is 0 of our current chunk, we can traverse up to left minus 1, where left is the leftmost index, because that's going to be the index of the completely empty prefix array. Once we get below that, then we can't traverse, and then we'll just cut there. So like if we're traversing 26k times here, we can only traverse once, and then when we traverse one more time, we'll be at -2, and then we'll just say like we're out of bounds, we're done. So we can cut it early there. And yeah, that's pretty much it, and it's also hard to code, so that's why I said this is nowhere near a medium problem, so let's code it up. So we're going to make this prefixes dictionary, and we're going to set prefixes at index -1. And so the nice thing about Python is you can just use a counter, which is basically a default dict. So we're just going to use counters. Now we're going to say left is going to be our left bound of our chunk, and our result is 0. So for our in range length word, then we need to compare the character to the previous character, right? So if absolute value of word at prefix or at index r minus word at index r minus 1, if r is greater than 0. If r is 0, then we can just like use the current word because we know it's going to be valid, right? So if we're on the first index, we'll just take the first index because that's always going to be valid. So we'll say it like this. It's going to be fine. You can also just like compare to a previous variable and set the previous variable equal to like the first variable in the list or something. That would work too. So essentially, if this difference is greater than 2, then we have to reset our chunk. So we'll say prefixes equals new chunk, and we'll say prefixes at whatever index we're at -1 is going to be an empty counter, which is just like an empty dictionary. So the nice thing about the counter or like a default dict is if you look up a key in here and it's not in there, it'll just give you 0 for the value, which is convenient. So now that that's the case, and then we'll also set the left bound of our chunk to be where we currently are if we did have to reset our chunk. Now the rest of it. So what we need to do basically for every index is we need to take the old dictionary that we had at the previous index, copy it, and then take whatever letter we are at and add 1 to it. So we'll say prefixes at index r equals prefixes at index r minus 1 dot copy. Right, we just want to make a copy, and then we want to add the current character. So prefixes r, word r. And like I said, you can probably write this in a more convenient way of coding. This is kind of annoying. So now that we have that, right, we have prefixes at the current index. Now essentially we need to loop back 26k times or until we're out of bounds, one of those. So we'll say for I in range 1 through 27. So this will be 1 through 26 because it's non-inclusive. And then we'll record the left index. So we'll say, not the best wording, but you know, bear with me. So left equals r minus k times I. Obviously, you can reword it better. So if left is less than that left boundary minus 1, then we're out of bounds and we can just break this, right? For example, if in our previous example, if we were on like index 2 and we subtracted 2k, now we were on index like -2, then left minus 1 here would be -1, so we'd be out of bounds. We can just break. Now, basically, what we're going to do is we're going to have a check variable that's just going to check if every single key was valid. So we're going to say check, we're going to initialize it to true, and then we're going to compare every key, and then if it wasn't valid, if any key isn't valid, we'll just break the loop and make check false. So left prefixes equals prefixes at index left, right prefixes equals prefixes at index right. And then for key in right prefixes, remember we need to check if the difference for every character in the right and the left is either k or 0. So calculate it, right prefixes, and we want to loop through the indices or the prefixes in right because in left there might not be any at all, right? So it's important to loop through the right ones, not the left ones. So differences right prefixes key minus left prefix key. And like I said, this is why it was convenient to use a counter, because even if it's not in here, it will just auto default return 0, which is nice for us. So if difference does not equal 0 and difference does not equal k, right, it has to be 0 or k, then our check is false. So this is not going to be a valid substring, and we don't need to look through any more keys, and we can just break this loop. Otherwise, if we were successfully able to go through the loop and check still remains true, then this is a valid substring, so we will just add whatever check is, right? So if check is true still, then it'll add 1. If its check is 0, it'll add 0. And finally, we can return the result. Probably made some mistakes, but yeah, okay. Let's see. Probably some kind of like, as well, not the best way of writing this, but whatever. Okay, so if absolute order okay. Oh, here we go. So this needs to be closed here. So it needs to be completely like this. I think that's correct now, right? Yeah. So essentially, we're saying take the previous character if the index is valid. Otherwise, it's always valid. Okay. And now we can submit. And this one, even if you submit and it's like reasonably good, it still barely passes. So yeah, just kind of an annoying one to do for sure. Okay, so there we go. So we do have fast. It's very slow. I think it's very slow for most people. So yeah, we can go through the time complexity, and we can go through the time complexity that I would give it and like the real quote unquote time complexity. So the time complexity I would say here is, because for every single index, you are going back only 26 characters, and that's the most it can be. And then for every single one of those, you're comparing only 26 characters. It's going to be O of n, right? Or you could say it's only O, but the realistic time complexity, like worst case, is if every character does exist and you're going back 26, then it would be like 26 squared times n, which is like 500 or something. Or that's probably more than that, but and then that's why it barely passes. And also you do have like all these constant variables. So your real time, like worst case scenario, is going to be like 10 to the 7th or something, which is like kind of close to failing. So I'm just going to write it as O of n, but you can also write it like this as well. Because essentially every time you're going back up to 26k, and then also anytime you do a comparison, you compare up to 26 characters. So that can be, yeah, like every time you go back, you do 26, and then times 26, so it's like whatever that is, like 600 or something. So for the space, so for the prefixes, I think this is just going to be O of n, because worst case scenario, like your prefixes is the entire array, right? Like let's say you have a bunch of you have an array of like only A's or something, or A's and B's or whatever, where you don't have any chunks. And then for every single index, you'll have, actually no, you can't have, no, sorry. This is never going to be O of n, because, can it be O of n? No, it can't be O of n. Yeah, I didn't check for that. Yeah, it can be O of n totally. Your count can easily be, your count for some index can easily be more than like k. Yeah. Like if your entire array was like A times a million, at least in the code I wrote here, we're not really checking for like having too many letters, because even if you have too many letters, you can still have like a bunch of substrings. Like let's say your chunk is like 4 A's and k is 3, then this is still this chunk still exists, because you like this is an array and this is an array, right? So just because your chunk is too big doesn't mean it's not valid, because you can just have a substring that ends with the last character, but that has like some characters missing from the front. So yeah, it's going to be O of n and O of n. Or yeah, you can also write like 26n or 26 squared n or something for time if you want to get more specific. Same thing for space. You can also write it as like 26n if you want to, because technically at every single index, you'll have a hash map of 26 characters. But because it's 26, I'll just write open. Yeah, so hopefully that was helpful. Like I said, I honestly think this was a pretty tough problem, and it's pretty unintuitive to figure this out. This all these simplifications to get all the substrings in O of n time, or roughly O of n time, by moving k back instead of just manually every single character and figuring out like what's the longest actual substring I can have that's valid. I don't think it's easy. So I think there are a lot of hard problems that I've done that are significantly easier than this problem. So definitely, if you weren't able to do this, totally fine. And I would say even if you saw this solution, I would still recommend coding it up because it's not easy. As you saw from here, like it's super easy to like screw a bunch of stuff up. So definitely a good one to code up, and I guess it would also be a little bit tougher in other languages because Python does have like counter and default dict and all those things. So if you were to do it in like JavaScript or something, it would probably be more annoying. But yeah, so hopefully this was helpful, and it was helpful. Please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.